Hello everyone, welcome to the Histology chapter 1 study along. Mm, I have completed this chapter few pages until the light microscopy. Let's continue further. Zoom in a bit more. I hope visibility is all okay. Perfect. So until now we studied that to study histology we need to in histology we study different types of tissues, their composition, their cells, their extracellular matrix, etc. We take a section of from a tissue, we prepare it and make it ready through various steps that we studied already uh, for us to examine and see the specimens under a microscope. Now, there are different types of microscopes and different types of uh, objects that we can use and to visualize. But common thing is light. Light is a phenomena that is used to observe all the specimens that we prepared. First type of light microscope is bright field microscope. This is the most common microscope that students use to study histological specimens in their med school. We also have some specimens that are transition electron microscope, but we'll get to that later. So, light microscopy, conventional bright microscopy, and more specialized applications like fluorescence, phase contrast, confocal, and polarizing microscopy are all based on the interaction of light with tissue components and are used to reveal studied tissue features. Bright field microscopy. With the bright field microscopy, stained tissue is examined with ordinary light passing through the preparation. As shown in figure 1.3, we'll go to 1.3 as well. So this is the figure 1.3. We'll come back. So as shown in figure 1.3, the microscope includes an optical system and a mechanism to move and focus the specimen. The optical components are the condenser, focusing light on the object to be studied, objective length, enlarging and projecting the image of the object towards the observer, and the eyepiece or the ocular lens, further magnifying this image and projecting it onto the viewer retina or charged coupled device CCD, highly sensitive to low light levels with the camera and monitor. The total magnification is obtained by multiplying the magnifying power of the objective and the ocular lenses. Okay, so this is a basic of what the structure of microscope looks like. These are basically the levers that help you to adjust the specimen and move it, and these are the basically components that are responsible for the visibility, the condenser here, so let's get into much detail. The critical factor is in obtaining a crisp detailed image with the light microscope is the resolving power, defined as the smallest distance between two structures at which they can be seen as separate objects. The maximum resolving power of the light microscope is approximately zero point 0.2 meter, which can permit clear image magnified 1000 to 1500 times. Now, what does exactly revolving power means? Revolving power means it's a distance between two objects in the specimen. Let's say there are two cells and they are separated at a distance of 0.2 micrometers. In case of bright field microscope, if two cells are separated at 0.2 micrometers, we will see them separately. But just in case they are anywhere less than 2 micrometers distanced, we are not able to see both of these structures separately. We will all see it as one structure. So this is the basis of what a revolving power looks like and how crisp the image will be obtained. So basically, revolving power is the maximum resolving power of a light microscope, which is zero point 0.2 meters, micrometers. And basically, so when it is so good, that is zero point 0.2 micrometers, you can magnify image up to 1000 to 1500 times, which can objects smaller or thinner than zero point 0.2 microscope, such as ribosomes or cytoplasmic microfilaments, cannot be distinguished with this instrument. Likewise, two structures such as mitochondria will be seen as only one object if they are separated by less than micro 2.0.2 micrometers, as I explained. The microscope's resolving power determines the quality of the image, its clarity and richness of detail, and depends mainly on the quality of its objective lens. Magnification is of value only when accompanied by high resolution. Objective lenses providing higher magnification are designed to also have higher resolving power. The eyepiece lens only enlarges the image obtained by the objective and does not improve resolution power. We know now the concept of magnification doesn't make that much of sense, because now we are dealing at something that is distance with zero point 0.2 micrometers. We don't need more of magnification to see anything that is less than, that is separated less than zero point 0.2 micrometers. There are some things like they mentioned about ribosomes and the cytoplasmic microfilaments, but they are not much of importance, and we if we need to observe them, we need to go to an electron microscope. So we have also virtual microscopy, typically used for study of bright field microscopic preparation, involves the conversion of stained tissue preparation to high resolution digital images, and permits study of tissues using a computer or other digital devices without an actual stained slide or a microscope. So basically, just to ease for students to study histology, and this happens in our university as well, that histology specimens are once prepared in the best possible way, are examined on the bright field microscope, and then the generated images are saved in an electronic form, in a digital form, and then you can zoom it, you can watch it, view it multiple times. You can refer this same single one generated image for I don't know how many years, and you have to just go through the hard process of preparing specimens and observing just once, and you have a digital image. This is virtual microscopy. Almost all universities use it. Our university also uses it to explain things in detail. In this technique, regions of glass mounted specimens are captured digitally in a grid like pattern at multiple magnifications using a specialized slide scanning microscope and saved as thousands of consecutive image files. Software then converts this data set of for storage as a server using a format that allows access, visualization, and navigation of original slide with common web browser or other devices. With advantages in the cost and ease of use, virtual microscopy is rapidly replacing light microscopes and collections of glass slides in histology laboratories for students. So also they have explained now how do we capture these images. So there are different softwares. We use Olivia, which is a software that has all the images saved, and like when you're observing, you can't take just one image, you have to take multiple images, place them, and there's a lot of editing that goes behind, and there's also a lot of softwares required that support this kind of image viewing. Imagine a zoom where you have to go zero point 0.2 micrometers of a resolving power. So we cannot have our normal image viewing softwares. We need something more advanced where we can go up to 1000 to 1500 magnification. So it takes a lot of work, I guess. We have another type of microscope, is a fluorescence microscope. When certain cellular substances are irradiated by light of proper wavelength that emits light with a longer wavelength, a phenomena called fluorescence. In fluorescence, we know what is fluorescence, right? In fluorescence microscopy, tissue sections are usually irradiated with ultraviolet light, and emissions is the visible portion of the spectrum. The fluorescent substance appears bright on a dark background for fluorescent microscopy. The instrument has source of UV or other light filters that select rays of different wavelengths emitted by the substances to be visualized. So a fluorescence compound can be visualized because when you put a ultraviolet light on it and we have a visible range, and the fluorescent compound will give you visibility. Fluorescent compounds with affinity for specific cells micromolecules can be used as fluorescent stains. Acridine orange, which binds both DNA and RNA, is an example. I think we should remember what kind of fluorescent stain is used, which is acridine orange, and which binds both DNA and RNA, is an example. So staining works differently here. Like for the for the bright field microscope, we saw that the staining, you can go with H&E staining, you can go with the Sudan black stain, so but they are not fluorescent stains. Where they had basic dyes and acidic dyes, here there is a fluorescent dye which is an acridine orange in case of DNA and RNA. When observed in the fluorescent microscope, these nucleic acid emits slightly different fluorescence, allowing them to be localized. check. How long has been there a no audio? Shit. Give me a second, guys. I'm just checking the audio. Why did this happen? My mic was off the whole time, or since now? I checked the mic actually at the start. Oh, there has been no volume since very long time. It has source of UV or other light filters that project rays of we visualize. So a fluorescence compound can be visualized because then we